Bismillahirrahmanirrahim. Assalamu alaikum everyone. I think you are be looking for the summary of the previous lecture. That was a bit technical, and we will not discontinue this discussion, but we will continue this discussion about the heteroscedasticity, and we will continue discussing about the different detection method, and at the end, as usual, we will be talking about some of the remedial measures. So starting from the summary of the previous lecture, what is the heteroscedasticity? Now I am only will be given one-liner definition and will be going further. Thus heteroscedasticity is when the variance of the error term is not constant over time. We say that there is a problem of heteroscedasticity. The immediate question arises that why heteroscedasticity comes into the data. The first reason, the first and the foremost reason is that there is an error learning situation in human behavior. In the beginning, we learn from the errors, and if you remember, I would like to repeat the same example that, for example, you start typing in the first hour, you are making errors more, and at later stage you are improving. The second may be that there is a skewed distribution of many of the variables in the population. For example, if you see, there is a concentration of wealth in the wealth and income in some of the hands in Pakistan. For example, the Zardaris, the Sharifs, the Mazaris, and the many other people. This was to name few of them. There is a different distribution of the wealth or income as compared to, it is not equally spread around the people of Pakistan. Similarly, if you go to for the education, you will see that in the Balochistan as compared to this Islamabad where we are sitting at this time, there is a different distribution of the education. So this is the second reason for the heteroscedasticity. The other reasons may be that your model is misspecified, and the other is you have less discretion in the beginning. I gave the example of the income consumption behavior, and or you can say the saving consumption behavior, saving income behavior at lower level of income. Your discretion is small. As the level of income increases, you become more freed about this. The other example may be that the many companies who have large profits, they are more they have more discretionary power in giving dividends to its people. So the other problem was our major concentration is on that what is the problem if heteroscedasticity in the data, and we saw this is much serious problem as compared to our previous discussion, that was the multicollinearity. In heteroscedasticity, you will come to know that our estimator that we estimated from OLS are no more below, and they are not now best. What this means, they are not the minimum variance, and immediately you will come to know that if there are not minimum variance, there are not small standard errors, and your the acceptance region in the confidence interval increases, and many of the time there is the probability that you are not going to reject the null hypothesis. Then the other issue comes that how we detect that there is heteroscedasticity. No rule of thumb there. Most of the time we will be talking about this, but fortunately I gave you some of the clues that could help you in detecting the heteroscedasticity. First were the formal methods, that it is from the institution, your expertise, your skill, that most of the time in cross-sectional data there is the chance that there is the problem of heteroscedasticity. Then there is a graphical representation, get the residual sum of square and plot it against the y hat, or if you are you feel easy, plot this residual sum of square against the xi's, you will come to know if there is systematic problem, then there is a heteroscedasticity, and if there is no systematic problem, you may accept that there is homoscedasticity. These were the informal method. We started looking at the formal method, and first we discussed that was the Park method, and the other was Glaser method. Both are similar to each other with a very small differentiation. I am not interested to give you the detail here. Now what we are going to cover today, As I think you have guessed that our discussion about the heteroscedasticity remained incomplete in the previous lecture when we closed up, but now hopefully we will complete this discussion in this lecture. And what we will be doing, we will be continuing about knowing more and more about the heteroscedasticity method that we started, that were the formal method. We will be just talking about 2 or 3 more methods, and then we will come towards the remedial measures, and at the end, as usual, you will get a brief summary of the today discussion. So starting from the formal methods, if you remember, we just studied 2 methods, that were the Park test and the Glaser method. The more interesting most interesting method of detecting heteroscedasticity is Spearman ring correlation. I may assume that you have learned this word before, Spearman's ring correlation, and it seems very plausible to write immediately this formula, because we will be concentrating on this and I will be explaining that what is this. So this is that R is the correlation and S is the Spearman correlation. It is equal to 1 minus 6 summation di square divided by n into n square minus 1. This is the formula for this. So this is the first of all, we will see that what is this D. This D is the difference. Look at this, we will be talking about and we will be calculating the difference in the ranks assigned to 2 different characteristics of the ith individual. The individual will be same, it would have 2 different characteristics, and we will assigning them rank according to their position in the data, and n is the number of individuals or phenomena ranked, or you can say the number of observation in the simple way. So this was the formula for the Spearman ring correlation, and what is it is used for, you should remember for this, although you should not be asked if for intensive you can say the mechanism, but you still remember that what purpose is the Spearman's ring correlation and in which case it helps you to find which problem. So it is a 3-step procedure. The first step is fit the regression on the data on y and x and obtain the residual ui hat. Now I will be writing the data because I have to show that how you would like to rank this. So first of all, I would be writing the supposed hypothetical data. It may be when I will be talking about the total or the calculation, I will be leaving it up to you because these will be very simplified calculations, and to save the time I will be ignoring these and putting it on your shoulder. So what is this? For example, this is the data, this is your consumption, and this is your income, that is the X. I say that I will just taking 6 or 7 value. This is 50, I say this is 40, this is again 45, 60, and I say that this is 55. This is the Y, and you can see these are the 5 observations, just to keep the thing simple. And what is this X? X is, that is the income, this is now the consumption, and this is the income. What is this? Income is, for example, at this 80, 100, I can say that is 60, this is 50, and I can say this is 90. Now what is the first step? In first step, regress y on x. I would like to write that it will be yi is equal to beta 1 plus beta 2 x. In this simple model, this is the xi. So what will be the, and what we will be getting plus ui, and we will be getting that yi hat is equal to beta 1 hat plus beta 2 hat xi. hat means the estimated parameters. So what this means, now what was the purpose of, we are interested to get ui hat, and you can immediately come to know that yi hat yi minus yi hat, this is equal to ui hat. So I will suppose here that I get the, first I will suppose that this is the yi, this is yi hat, just supposing, and I say that is this is 60, I can say that this is the 55, I can say this is the 40, this is the 60, and this I can say that this is the 70. So what is now I can calculate ui hat. Immediately you will, this is ui hat, yi, this is yi minus yi hat, this column minus this column. So what is this? This is minus 10, this is minus 15, and this is, if you see, plus 5, this is 0, this is 60, this is 0, and this is, you can again say that this is minus 15. So this is the ui hat. This was our first step in the, you can say, the Spearman rank correlation. What will be, if you see, this is the fit the regression line. We fitted the regression line on the data y on x. If you can see, this is, we fit this regression line on this, and then obtain the residuals ui, that is the error term, residual, disturbance term, whatsoever you can call, this is ui hat, and this is simply yi minus y hat. Now this was the first step. Now there is the step 2. What is the step 2 here? Ignoring the sign of ui hat, rank both ui hat and xi or yi hat. First we ignore the sign of ui hat. I would like to just change it a bit, because when I will be ranking it here, let me make it 69 so that it becomes 14, minus 14, just to differentiate from 15. No other reason behind this. So I am ignoring the sign, and ui hat I am writing in this way. This is now ui hat. This will become positive, positive 5, 0, and this will become also the positive. So this is the second step. We have taken the ui hat. Now our purpose is not done. Purpose is that we should rank both ui hat that we have just completed here. This ui hat, if I say this is, I am writing column number 1, 2, 3, 4, and 6. I have to rank column number 6, and I have to rank the column number 2, or I can even rank this is, that is the yi hat. It is up to my discretion that which I do. There will be no difference whether I rank this. Now ranking is that we should not change the ascending or descending order. We should keep in mind the descending order and write only the figure, that what is its number. I would like to give you, so I would like to calculate, rank this. So I am ranking rank ui hat, this column ui hat. Look at this, 0 is the minimum. 0 is the minimum, I would write 1 before this. In this line, I am now going as a ascending order as from the first one. The lowest value is 1. 0, that is the lowest value, and I will be giving it the name 1. And what is the 2? You will immediately come to know that this is getting 2. If you see that this is the 3. This is 14 is the 4, and this is the 5. So I have ranked the ui hat according to the ascending order. मैंने ui के वैल्यूज को चेंज नहीं किया, उनका जो रैंक था उनको मैंने जो है वो उसको जो है वो रैंक कर दिया है. फॉर एग्जाम्पल if you write it in ascending order, 0 it will become 0, 5, 10, 14 and 15. So look at this 1, 2, 3, 4 and 5. Look at this 1, 2, 3, 4 and 5. Similar thing. But here there is some purpose. In the same way, we would like to rank the xi. So this is rank x. If you remember, where is your x? This is the second column. Which is the lowest value? This is the 60. This is the 50 is the lowest value, and this will become 1. This is by incidence that this is against 1 and 1. Otherwise, no specific, or you can say that I have not taken something special into consideration. It is just randomly. I am doing it just randomly. This is the lowest value. After this, if you see, this is the 60. This is 2. What is then? This is the 3 is. This is the fourth is. This is the fourth. And this is the fifth. So there is some, due to this, there is some problem, because now as I am going to take the difference, if it was although random, but it created some problem. So what problem is, now I have just to change it. I will see it that it is 89 rather than this is. I would like to say that this is not 80, this is 90 and this is 80, just to say, and this will become 4 and this will become 3. Now because I have to take the difference of between these two columns, if the previous situation remains, the difference will become 0. So what is the D? D is the difference. If you see, difference between the ranks now. This is -1, this is 0, this is 0, this is 0, and this is 1. If I keep the previous situation, there will be always 0 and we may have some problem. So what is this? In the real data, it can't happen that there is some systematic trend. Although I did randomly, but I think something is in my behind my conscience. There is something systematic trend that it was you can say incidentally equal to this. So what is this? I want to take the difference of these two columns. This is 7 column and 8. So this is the result of 7 minus 8 column. So this is 3 minus 4 minus 1 0 0 0 and 1. So now I need, if you look at the formula, I need D square. So I will simply make the square. This will become 1 0 0 0 1. And what is the summation di square? It is simply equal to 2. 1 this and 1 this 2. So now if you look at the formula, you can see we have almost calculated each and everything. So I have to just you can say the replace the thing. Go to the formula again. This is the formula, and now RS at the formula is written here, that is at the top. Is RS Spearman correlation 1 minus 6, and you have calculated summation di square 2 over n is number of observation 1 2 3 4 5. 5 into 5 square 25 minus 1, and this will become minus 5, and this will become 2 over, you can say, 120. This will become 24, and when we will multiply 24 by 5, it will become 120. So it will become equal to minus 10 over 120, and whatsoever it will become minus 1 over 12. Again, I would like to apologize if there is some calculation mistake, because I am not interested into this. The second process is completed. This and that is the Spearman correlation. Very interesting to detect the you can say the heteroscedasticity. First run the regression. The other is get the residual sum and now rank them according to this. In some of the test we will be saying rather than ranking we will changing the values ascending or in descending order. We are ranking all these values either in the descending order or in the ascending order. We started from the ascending, the minimum value got the rank 1, the upper 2, and the maximum value got the latest ranking. So now what do we have to do? This is the now step 3. Significance of RS can be tested by the test as follows. This is another formula and we have to show that whether what we have calculated RS is it equal to our T statistic, and T statistics is T is equal to RS into, if you see the formula, n minus 2 and divided by 1 minus RS square under root. So now substitute the value. What is the RS? Minus 1 over 12 into n. What is this? 5n minus 2 under root, and this is 1 minus 1 over 12 whole square. So this is equal to T. Now I will not again test, I will not estimate this, and it will be your responsibility to calculate. Now I am going to tell rule of thumb. If the computed T, here we have computed T, if this computed T, now go to your rule of thumb of the previous when that we discussed in the, you can say, the hypothesis testing. So what is this? This is the now the calculated T that you have calculated from this formula. As I was going randomly, so these were values. You can calculate all this term. This is, and you definitely you will come up some of the value. And when you get the, this will be T calculated, and if T calculated exceeds the critical T value at this, for example, if your this T calculated exceeds the value of T tabulated, definitely at this degree of freedom and the confidence level you may have you definitely have some T value. We may accept the hypothesis heteroscedasticity. What this means, our null hypothesis was again same. In the test there may be change in the null hypothesis, but in Spearman rank correlation we again make the null hypothesis that there is no heteroscedasticity, and you know we reject the null hypothesis when our T calculated is greater than T tabulated. So if this calculated T is greater than your T tabulated, we will say, we will suspect that there is a problem of heteroscedasticity, and if T calculated is less than T tabulated, we are unable to reject the null hypothesis, and we will say that there is no problem of heteroscedasticity, or we will say that there is homoscedasticity in the data. After this, the next is the formal methods. There is Goldfeld Quandt test. This is the fourth formula, started from the Park test, Glaser test, Spearman rank correlation, and now we are in the Goldfeld Quandt test. What the Goldfeld? Very popular method, and it is even more popular, and it when we assume that the independent variable and the sigma I square, that is the variance of the error term, are positively correlated. So what is this? If we look at this, that we assume one of the explanatory variable कि आपके residual sum of square, that is your variance of the error term, and any one of the explanatory variable 1, 2, 3 or only one, there is a positive relationship between this. So what will be the order or rank the observation? It starts from the first of all, rather than making the OLS regression or doing something else, it immediately starts order or rank the observation according to the values of the xi, any of the variable that you suspect that it has something common, or you can say some link with the error term, error variance, beginning with the lowest x values. Now there is compulsion, we can't do it descending or the ascending order, but we are now bound to rank the values as the ascending order. So what is this? I would like to give you, take again some of the example. These are the x values, x, this is the y. Rather I should take y here and I should take x here. What is this? Again the same definition. One is the consumption, y is the consumption, x is the income. Now I will be again randomly taking, this is 40, 30, 60, I will be taking 7 values this, and 50, again I 45, and this is 70, and I can say that this is the 80. Randomly I have taken. And this is x, I say this is 100, 150, 120, 105, 160, 100, 100. To avoid this, I will see 120 to differentiate from this 120, and this is, I will say that 110. Now if you see, there are 7 pairs of the accent values. So now in what Goldfeld Quandt test, the first is order or rank the observation according to the values of x. We will be first taking x values, and against that values we will be changing the y values, because we will not only be taking the ascending or descending order of the x, but according to this we have to change the values of the x starting y starting from the lowest x. Look at, help me here. Now I will call this that the ranked. Now these are ranked, and I would like to show it that this is ranked y, and this is x. And I have to differentiate it from here. So what is this x? Now go to only the column x. This is column A. Take the minimum value first. Fortunately it is 100. The next is 105. This was the first. The other is 110. Then there is 120. These are two 120s values, so I would like to make it 125. 110, this is 120, 125, and 150 and 160. So now I have ranked, let me count the values. These are the 7 values. So what is this in the this Goldfeld Quandt test? Very, very important test, and it is very useful in detecting the heteroscedasticity. Now I have ascendingly arranged rather than ranked, arranged the values of x. Now look at this. When the x was 105, I should write the value of y here. When it was 105, the value of y was 50. So I would like 50 before this. When x was 100, look at this, y was 40. This is the first pair is the same. When x was 110, look at here, this is 110, the y was 80. So 110, this is 80. When the x was 120, look at this, this is 120, y was 70. When x was 125, this one, x was 60. When it is 150, look at this, the x is, the y is 30, and when it is 160, look at here, it is 45. Now I have arranged the x values in ascending order, and against these values there are also the arranged values of x x that are not necessarily true, that they are in a position ascending or descending. We are just concentrating on the x. Look at this. Our first step is over. This step first is clear. The other is omit the central observation. C is the central observation, where is specified from the C. This is omit the central observation looking at the x, and definitely we will be omitting it from y also. Whereas C is specified priori. Keep in mind that how many observations we have to omit from there, because now we want to differentiate data into two parts. First part we will be calling it with smaller variance, at it is a ascending adder, and the second part will be, we will be calling it that this is a part that has a higher variance. So what is this? When we will omit this, the remaining values we will group this, the n minus c observation, आप जब उसमें से c निकाल देंगे बाकी n observation रह जाएंगी, into two groups, two equal groups. So what is this? Come to here, help me again. For example, if I take that I will omit this c, and I assume that I will omit only this value. I will be talking about later that there is a huge discussion that how many values have to be detected. Some people say that again if there are 30 observations, we should detect 5. The other do not agree, but everyone is giving his or her estimates. But what I am only omitting one value here, the reason is that I have just taken 7 values and I am omitting it 1. Now I have differentiated data, delineated data into two groups. There are first 3, these are 3 values, and these are also the 3 values. Now there are 2 groups of data, so you can say this is the first group. I would like to write it first here, and this is the second group. Now what is the third step? Fit separate OLS regression. Now we have to run the OLS regression on both groups. अब हमारा डाटा 2 ग्रुप्स में आ गया. We have to run the OLS regression to the first group and the second group. Okay, come here and we run the regression. So this is, what is this? We will be doing OLS regression, and regression will be very simple, that yi is equal to beta 1 plus beta 2 xi plus ui, and when we will estimate it, it will become yi hat beta 1 hat plus beta 2 hat xi. This will be the first group. Similar things we will be doing. We will be applying the OLS ordinary least square, and we will be again same scenario, that we will be estimating yi hat is equal to beta 1 hat plus beta 2 hat xi. What is our purpose of doing this? From doing all this, we will be getting residual sum of square. If you remember that the total sum of square is equal to explained sum of square plus residual sum of square, that is the unexplained proportion. So we will be getting one residual sum of square. This is residual sum of square, we will call it 1. And from this, now formulas are with you, you can get this, and this is residual sum of square, and this is the 2. Now we have come up with 2 residual sum of square. The first residual sum of square is related to the group of data that has the lower variance. Why we are saying this? How we come to know that it has the lower variance? The logic behind this is, as data is ascending, and in the first half of the data is small as compared to the later half of the data. So we have got this, and now let's see what we have to do. Now smaller xi, and this is, these residual sum of square each have n minus c over 2 minus k degree of freedom. Every time this has degree of freedom n minus c over 2 minus k, and this have been calculated on the same way, n minus c over 2 minus k. You know n is the total number of observation now in the one group, not in the total numbers of observation, that is the 7. What will be this? N is here 3, in this group 3, and C you omitted one value, that is 1, so 3 minus 1. And what is the K? Number of parameter to be estimated. So these are 2 parameters here as well as 2 parameter here. So if I want to calculate the degree of freedom, what it will become? N total number of observation minus 2 and minus K is equal to also, that is the 2. This way we will be calculating the degree of freedom. So on this, when we will calculate this degree of freedom, now what is the fourth step is compute the ratio. Now you have 2 residual sum of square. Now we can compute the ratio, and what is the ratio? We will call it the lambda. This is the fourth step. Compute the this is a residual sum of square of 2, this value, and with the same degree of freedom, and it is divided by a residual sum of square 1 with the same degree of freedom. We have calculated the degree of freedom. Now we are at the end of this test, and what we will be showing this, that look at this. Now we have calculated this. Now there is a value of lambda. If an application, the computed lambda, look at this, the computed lambda f, it is equal to f. F is a test and it has a distribution. At some time in the future lecture I will be flashing back to this f, because I know that I have just explained the z test, the z distribution and the t distribution and the t test also, but I have not yet explained the f test. F test is very important, just giving to one liner definition here, that it helps us to test all the parameters simultaneously, but in t-test we test beta 1 separately, beta 2 separately, beta 3 and so on. But in the f-test it has the potential that it can test all the parameters in a simultaneous way. So I am not explaining here, but I have just given you the idea that f-test has its own distribution. So now lambda, assume that this is the calculated value of the y. If lambda is greater than the critical f at chosen level of significance, for example, we choose level, we have the degree of freedom now, we can choose the level of significance, we can reject the null hypothesis of homoscedasticity. For example, if this lambda, now I will call it f calculated, it is greater than f tabulated, what I will see that reject h naught. And what is h naught? H naught is that there is homoscedasticity. There is homoscedasticity. There is homoscedasticity, or otherwise I can say that there is no heteroscedasticity. So if f calculator becomes greater than f tabulated at given level of significance as well as the degrees of freedom, we reject the null hypothesis and we say that there is a problem of heteroscedasticity in the data. In this, doing this, we have completed the Goldfeld Quandt test. That is very important. So things to remember, something you have to remember, that what the choice of C value is critical and debatable. As I said in the beginning, we can't say that how many observation we should omit from the center of the data, 1, 2, 3, 4. There is some proportional guess as given by some of the people, that most of the time we remember that if it is equal to 30, most of the time we omit 4 or 5 things from observation from the center. If more than one independent variable, this was the case of one independent variable, if there are, because if you remember we ranked according to x, there was only one independent variable. But what the situation is, if more than independent variable, no need to worry about, you can arrange the values about any of the, with respect to any of the independent variable, that observation can be made according to any of the xi variable. So this was the fourth, but there is a still very general test of heteroscedasticity. This is very important. Every time I am saying that this is important, each test is not, you can say, inferior than the others. Every test has its own significance, and every test performs well in some of the specific circumstances. You may be thinking that why there are so many tests, because different tests performs differently, and sometimes in a better way, and sometimes you can say not in one test becomes a failure in some kind of special situation. Why test? It is easy and does not require normality assumption. It has two very interesting things. In the previous test that we have just completed, that was the Goldfeld Quandt test, we assume that our error terms are normally distribution. Every assumption is good assumption, but it puts some restriction on the behavior of the variable. So if we can go without the, you can say, if we can go without any of the assumption, it is better as compared to if we go with many assumption. But it doesn't mean that the assumption are unnecessary. If there is no way out that we could go, we need some of the assumption. This is the white test. It is not the white color, it is a name of a person that was the white. So what is this? In the first step, estimate the equation, this one. Now I am assuming that there are two independent variables, x2 and x3. I would like to write it here. So what is this? This is yi is not now equal to, if I would like to write, there is no space, I would have to write it here. Yi is equal to beta 1 hat plus beta 1 still not estimated, beta 1 plus beta 2. Again, apologize for the not fully command on the electric pen. Beta 2 x1 x2 plus beta 3 x3. You will be thinking that where is the x1? I am showing that x1 is here and its power is 0. And as its power is 0, it is equal to 1. We do not write it with beta 1 plus ui. If yi is equal to, now what we'll be doing, this was our original model, so we will estimate this model. So we will estimate, it will become yi hat is equal to beta 1 hat plus beta 2 hat x2 I means values plus beta 3 x3 I. So this is the value. Run the following auxiliary. The first step is over. You simply ran the regression of y on two independent variable. Run the following auxiliary. Auxiliary regression, you are well aware of that in multicollinearity we also use this word, the auxiliary regression. So what will be doing? We will be running auxiliary regression ui hat square. So from where we will be getting ui hat? You know that ui hat is equal to yi minus yi hat. Now I am not using the data to just confine myself and to save the time. So this is ui hat square. We will have to now run on, what is this? We will be beta 1 plus beta 2 x2 I plus beta 3 x3 I plus square of both these x2 beta, we will be calling it beta 5. I would like to write further it beta 4 x2 square plus beta 5 x3 square plus beta 6 x2 x3. Now look at this. We have taken the square of it. Look at this. Now you can call it the alphas. To just differentiate, even you call it the betas, because we will not be going to the previous equation. If you are interested, you can use other notation, that is the alpha 2, alpha 3. And look at this, from here we have started taking the square. We are taking the absolute value also of the same variable, and we are also taking as independent value of the same variable as a square. So here is the square, and we are going one step further, that we are taking the product also. So this is the regression that we will run, that is called the auxiliary regression. Auxiliary regression in we are regressing it on the UI hat. UI hat are being regressed on x1, x2, x3, x2 square, x3 square, and x2, x3, the product. The step 3 is under the null hypothesis. Now I am just giving you that this is by assumption. Under the null hypothesis that there is no heteroscedasticity. If we making the null hypothesis and we assume that we have made this, that there is no heteroscedasticity, this n, the number of observation, multiplied by the r square obtained from the auxiliary regression. We may have r square from here, we may be r square definitely from here, and we asymptotically follows the chi-square distribution. We say, what is this step? This is a, you can say, bit technical. In we are showing that we will be testing our null hypothesis by the chi-square distribution. And if we assume in this auxiliary regression that our null hypothesis is that there is no heteroscedasticity, or the same thing I can explain that there is homoscedasticity. So this follows under this assumption that n multiplied by r square in asymptotically in the large sample, it follows the chi-square distribution. Now we have supposed that this follows the chi-square. If the obtained chi-square value, now we will be getting to, as formula, we will be getting obtained chi-square value exceeds the critical value. So look at here. If we get the chi-square, that is the calculated, we have given this formula previously, and it is greater than the chi-square, that is, you can say the tabulated, or I can say that this is the critical, not tabulated, critical, then what is this? We can conclude that there is no heteroscedasticity and vice versa. If we reject the null hypothesis, there is heteroscedasticity, and if we can't bring enough evidence against this, the rejection of the null hypothesis, we say we are unable to reject the null hypothesis, and there is homoscedasticity in the data. So you will be looking that I have avoided giving you the formulas of this. These are the formulas with you previously. Here degree of freedom is with you, level of significance you have, you can use this you can calculate, this you can take from the table, and you can compare them, and you can reject or the null hypothesis. If you see that these were the 5 tests of heteroscedasticity detection. So if there are 5 tests, it doesn't mean that there are no more tests, but fortunately be happy that I am not going to explain these tests. It is just the limitation of the time and the less importance of these tests. But keep in mind, in special circumstances, each player is a very good player. For example, on the spin wickets, you can say the spinners are good, but in South Africa, as happened with our team, the fast bowlers perform well, as Dale Steyn did with our team. So this is Bruce, Pagan, Godfrey test. This is also used for these 2 tests. You should only remember one thing, that these tests are used for the detection of the heteroscedasticity, and it is also the KB test, that is Conker-Bassett test of heteroscedasticity. Now you are in a well position. I can presume, and I am dead sure that you will immediately detect that whether there is heteroscedasticity or not. Now you will be getting some clue from here that in practical life you have not to do all these things, because when you will be doing analysis on any of the statistical software, you will go some of the options, and it will be giving you the test of heteroscedasticity, and you will be looking at the values. You should be only compare the calculated and the other values, and it will be giving you the p-values, and you know p-values is the probability that whether we can reject or we can't reject the null hypothesis. So the immediate question you will be making, that why there is so rigorous practice of this. I would like to give the example that if you the computer can make plus, minuses, multiplication, squares, then why we teach you in the beginning that how to add the terms, how to square the terms? Because you would have something aware of, that is what is happening behind the curtain. Because if you are just, you have a surface knowledge, sathi knowledge hai aapka, then if there is any of the problem, if it is good, if everything is going well, you are going well, but if there is any of the problem, you may have some of the critical consequences. So that was the reason behind this. So what are the remedial measures? We are not such kind of the, you can say, the diagnostic person that we only diagnose that the data has this problem. We give you the solution, because if solutions are not there, the detection loses its importance. Under heteroscedasticity, OLS are no efficient. You know this, I need not to explain. They have no minimum variance. This makes the usual hypothesis testing procedure of dubious value. Dubious values means, as these are not minimum variance, your confidence interval will increase, and the confidence interval of accepting the null hypothesis will increase, and there will be small probability that you are going to reject the null hypothesis. So what the remedial measures are, two approaches are done for this. The two approaches for this that are, we call that these are the remedial measure. When sigma square is known, we suppose that sigma square is known, this is the variance of the error terms of the population. You will be laughing and thinking that we are not aware of this, but when we are aware of this, we suppose we are aware of this, we use different techniques. You are right in supposing that this is rarely known, and we will be talking about when it is not known, then what will we be doing this. The first is when sigma square is known. Assumption. If sigma square is known, then the simpler method is the weighted least square method. We give the weight. If you remember, it is not, and you can say the similar or the identical example, but it is similar, that if when we transform the variable to avoid the multicollinearity, and we divided all the variable by total population to get per capita of the variable, similarly we will be dividing all the variable by sum of the weight. The OLS estimator become below. If you will be taking these techniques, for example, you diagnose that there is a problem of heteroscedasticity, you can use the weighted least square method. And if you will use the weighted least square method, you will come to know that your parameter becomes, that were not below in case of OLS, now you estimated by WLS weighted least square method, now they are below, because now they have the minimum variance among the competitors. So what is this? Run the following regression. Now what is, before this, what is the regression? The simple regression is, now this is yi is equal to beta 1 plus beta 2 xi plus ui. Now what we say that we know that the sigma square I is known. We divide all the term by this. This will become yi divided by this sigma square, that we say that this is known to us. Sigma square I is equal to beta 1 over, you can write it even, sigma square I plus beta 2 xi over sigma square I plus ui over sigma square I. So if I call this, that this is the beta star, this is beta 2 star, so this will become yi star, just to make the thing simple. So this whole term I am writing it yi star, and you can write it that what is, it is equal to yi star, this is beta 1 star and this is the plus. This is plus beta 2 star xi star. Now xi star means that you have it has been divided by this, and this shows that we have estimated this. Rather than saying beta 1 hat, I have called it beta 1 star. No special reason behind this, but just to save that the differentiate the things. So this is the situation. Now if I think, look at this, this is a hypothetical your output. There was a model, you estimated this model, that was this one, and this is the output. This is beta 1 hat, this is beta 2 hat, this is the standard error of beta 1 hat, this is standard error of beta 2 hat, this is the t statistics, and this is the t statistics for this. Look at this, you use this model. Rather than star, this model has been written in this form. You can see this form. So what is this? You can again see this, that these are the standard errors of the parameters, and if you see that now these are the t statistics and this is the r square. Now you have obtained your, in this situation, when you estimated by OLS, your parameters were not below. But if you will give this output, now your parameter that you have estimated from weighted least square, now they are, you can say, the below. So this was the method of weighted least square. And the other is when sigma I square is not known. Most of the time it is unknown and it is rarely known. White heteroscedasticity, consistent variance and standard errors. So why I have given a mechanism in which it corrects the parameters with respect to the heteroscedasticity. These are called the heteroscedasticity consistent variance. So it means Mr. White is helping us a lot in detecting and removing the heteroscedasticity. These are also called, when we will be correcting these according to the White given criteria, these we will call that the heteroscedasticity corrected standard error, and there is a third name for this. This is a robust standard error. So three names. The first is White heteroscedasticity consistent variance and standard errors. The other is this one, and this is most important. This is the robust standard error. If you see here, now you see here, this is the Y, this is the model, and from here to here, this is an output of OLS. This is the output of OLS. This is something you can say that is making confusion here. So when White did this, according to White criteria, this is output from of the statistical software. So White standard errors are now corrected. And interestingly, what happened this is a very critical point here. If you look at the standard error when you estimated it from OLS and you did not corrected it for the White's, you can say the robust standard error, look at there, here standard error are very small as compared to here. In the White correction, standard error become very high. But look at this, the t values here, that your parameters are significant, but when you correct it, these become insignificant. Look at this t value, look at this t value, and look at also t this value. So what is the message? The very, very interesting message from this. The message is that if we do not correct our parameter when we are making that it is unknown, we can correct them and we will call them that now our standard error are robust standard error. It is corrected by some of the mechanism in which we are not interested. You will have been given the output. You will be seeing that sometime I am using that we need not, and sometime I am giving you some explanation. The reason behind it is this, that here there is some complex mathematics that I think we should avoid at this stage to avoid some of the more, you can say, the complication. So this is what is the message from here, that if you do not correct your parameters in the presence of the heteroscedasticity, you may say that your results are significant, but in reality they are insignificant. Look at here again that your everything was significant here. Look at this t statistics, this, and I think this t statistics should be here, so I will be writing it 3.06. so when it is more than 2, we say that the results are significant. But look at here that when you corrected, when you made it the robust standard error, you came to know that the problem has overwhelmingly changed, and when you were happy that the results are significant, now the results are insignificant. So I think it's time to give you the summary of the today lecture. We have completed our discussion about the heteroscedasticity, and I would like to give you what we started. We started our discussion from the detection method, and the first detection method we started from the Spearman rank correlation. I have remembered the formula that RS, that is the residual sum of square, is equal to 1 minus 6, and in the bracket there is summation di square divided by n into n square minus 1. So just give you some of its mechanism I have discussed in detail. So what this means, that first of all we run the regression, we get the UI hat. UI hat we get, and we also have the xi as well as the yi hat. We can rank UI hat with yi hat, or we can rank UI hat with xi, and I think you remember that we used the second approach, we rank the UI hat and the xi. The students become confused that we are not ascending, arranging the values. We are just looking at the values, and against each value we are writing 1 if it is the lowest value, and if it is the highest, going 1, 2, 3 and 4. And when we will arrange these two ranks, UI as well as the xi, then we will take the difference, that will be called the di. We will take the square and we will measure the rank, the Spearman rank correlation. Our purpose was not to just measure the rank, the correlation, Spearman correlation coefficient, but now from this we will be calculating the t values. And simply speaking, in all the tests, our null hypothesis was that there is there is no heteroscedasticity. And if we reject the null hypothesis, we say that there is heteroscedasticity, and if t calculated is greater than t tabulated, we will say that we reject the null hypothesis. After this, we tried the Goldfeld Quandt test. That is the very interesting. In this way, we in this mechanism, if you remember, that we arrange the values and we in the ascending adder, and we cut the sum of the values from the middle. C values, we divide the data into two portions, and the first portion we call that this is the residual sum of square 1, and the other is that this is the residual sum of square 2. We all get this from the regression, running the regression. If I go to the steps, I may make you confused, because if there is no data, I am just telling you the story, you may be confused. Just look at this. The ultimate purpose was to see the ratio of this, that was the lambda, and indirectly it was the F test. So what this means, the lambda was the residual sum of square RSS2 divided by RSS1, 2 and 1, the groups, we divided data into two groups. So if the calculated F, this lambda is, we suppose that this we are testing it by the F, and I will again assure you that sometime I will lash back to on the F test, and I will be telling about what is the F test. So if the calculated F value is greater than the tabulated F value, you reject again your null hypothesis. Now I will not see what was your null hypothesis. So if you reject, there is heteroscedasticity in the data, and if you do not reject the null hypothesis, there is no problem of heteroscedasticity in your data. Then we talked about one of the tests that was, if I remember, that there was the remedial measure rather than the test. In remedial measure, I skipped one of the tests in which we run the auxiliary regression. I am going to what is the remedial measure. The first is when the sigma square is known. When the sigma square is known, we have some techniques, but when the sigma square is not known, we may take some of the other techniques, and you know most of the time our sigma square is not known, and when our sigma square is not known, we are taking some of the residual measure, and you know we are using when it is known, we are taking the WLS weighted least square, and we are looking at this. When we apply the weighted least square, you know now what is the weighted. Our OLS estimator that were not below in OLS, now they become below, and we are happy. And when the sigma square, that is the error of the variance term, is known, then we applied the other technique that is called the white robust standard errors, or you can say that these are corrected for the heteroscedasticity. And when these are corrected for the heteroscedasticity, in the example you saw that when we calculated it by the OLS, there was high T statistics showing that your results are significant, but when we corrected it by the standard errors by using the white mechanism, we came to know that the T statistic became insignificant. So this was the message from these test, and this was the summary from today's lecture. So till in the next lecture we will meet, and until that, goodbye and Allah Hafiz.